Okay, welcome everyone. We're very happy to have Ebrahim Karimi for our Institute for Quantum Studies seminar speaker this week. I just wanted to give a brief introduction before I hand the floor over. So Ebrahim comes to us originally from Iran, and he is currently in Canada at the University of Ottawa. He is the research chair in structured quantum waves and also co-directs the University of Ottawa's Quantum Institute. Right. He's a very prolific scientist, experimental physicist, and expert in quantum optics. He's published over 170 papers, 3 patents, and has many awards. He has recognitions from Optica, the Optical Society, the Global Young Academy, the Royal Society of Canada, a fellow of the National Research Council of Canada, and Max Planck Institute for the Science of Light in Germany, and has many awards: the Ontario Early Researcher Award, the Early Career Researcher of the Year, the Hertzberg Medal, the NSERC Alan McDonald Fellowship, and more recently, the Rutherford Memorial Medal. So after all those awards, we're expecting a lot. So very happy to have you here, Ebrahim. It's already been a great visit, and so much looking forward to your talk.
Thank you very much, Andrew. And of course, Sean, other colleagues, it has been an amazing, the past week was amazing, and I really enjoyed the conversation and the meeting. And also thank you, Sarah. I know that you are there and for arranging the seminar. So thanks a lot for the kind introduction. I'm giving an overview about the field that we contributed significantly during my master, I would say, and then PhD, and also master and postdocs. And I would say that I all started from, maybe this is the first time that I'm saying in public, that all started from a letter from Emil Wolf. So we were doing an experiment. I was trained as a mathematician. I'm trained as a high energy physicist, but then I realized that we have a problem that it calls phase singularity or phase anomaly in the tight focus beam. So then I read a couple of papers by Emil Wolf, and we wrote an email to him and no reply. And after a couple of months, we received a package from him with a lot of papers and his handwriting that it got me interested in the field of singular optics and later on in the field of quantum optics. So we are all connected somehow to the Rochester. So I start with the structured quantum waves is a mixture of the electrons and photons. And first, I start with photonics perspective. So when we talk about the structured photons, well, we can somehow convince ourselves that photon has a wave function, though it doesn't have a rest mass. So it's not a solution to the Schrodinger equation, but we can write Riemann-Silberstein equations, and we get something like a Schrodinger equation. And it's beautiful. And then we can say, well, you can talk about wave function, and when you do the second quantization as well, you can label a single photon, the quanta of light, with either frequency, or you can play with label it with the polarization, the statistic of the photons, if they are coming as a Poissonian distribution or sub-Poissonian distribution or super Poissonian distribution, or you can even label them in a spatial mode. If I had a laser pointer, for example, usually we are familiar with the Gaussian profile, but this is not the only solution. So each of them, in mathematical perspective, they are assigning us a vector space or Hilbert space. For example, polarization is bidimensional, so is an excellent choice to send 0 and 1. But if you go, for example, to frequency domain, which is what they do in multiplexing, is infinite dimension, continuous variable, and you can use whatever you want there. So there are, in the lower case, I'm sorry, I don't have a pointer, I cannot use my scroller to show you that. In the lower side, you can see a few examples with the donut shape. This is what we call it, the beams that carries orbital momentum, which I will talk about it in depth, with a certain polarization distribution, or you can go even with 2 superposition of different orbital momentum and also polarization degrees of freedom. This is what you will get, vector beams. It has a lot of application in the microscopy. And or the other one, the third option, which is a pizza-like one, so you can have a certain distribution for photons and also certain point-by-point polarization distribution. And the fourth one also is another example. So the last three cases, they are very complicated topologies. And moreover, if you expand the Hilbert space, people, they call it classical entanglement. I don't like it. Even Bob and I, we wrote a science paper just to say people don't use the word of classical entanglement because it assigns only to quantum language. But also, apart from definition and using them, they are excellent in metrology applications. Why we care about them, as I say, they provide infinite dimension or unbounded dimensions, such a way that you can use them, for example, sending information in a secure fashion. For example, on the upper curve, you can see that these are what quantum bit error rates that you may have, and that's what the secret key rates that I talk about that when you do quantum communication. If you use the 0 and 1, the two alphabet that we do have, essentially the errors, if it goes to 11%, you cannot establish any positive key in standard BB84 protocol. But if you go to higher dimension, let's say dimension 16, for example, you can go even to 35% error in the system, and you can even send positive key rates. If you don't have a let's say error in the system, the key rate also increases logarithmic in the system. Or you can build up a device that can simulate very complicated physical system or chemical system, like let's say 2D materials, 3D materials, or certain molecules, which is very expensive if you want to do it with the classical computers. So having access to all of those alphabet, they are extremely important. So the first thing is orbital momentum, which I love, and essentially, I don't know if I have the definition here. Even if you go to Wikipedia page, this is what I made in 2009. The Wikipedia page for orbital angular momentum. You can create, apart from the Gaussian that you have it in the middle with L equal to 0, you can create beams that carry orbital momentum of 1 or -1. These look like a staircase. If you look at the face of them, they look like the staircase, and the dimension that you can see them, they are about the wavelength. So for example, if you go with 800 nanometers, if you do a full turn in the phase, you will get about 800 nanometers. So they have application, as I say, in a trapping, what we call optical trappings, or you can have application in quantum communication or even in classical communication. So for example, these have 7 dimensions. So I can send a single photon that can be in either of those states. And since they are mathematical orthogonal to each other, and also in the lab, you can get orthogonality between them. You can send, let's say, 1 out of 7 information that you want. And also, of course, you can have a mutual unbiased basis, which in this case is a prime number. You can have 8 mutual unbiased bases, and you can change the strategy as you wish. An example of this is a pasta fusilli. It's a double helix, essentially. And that was one of the reasons that I decided to go to Italy to do my PhD. Though the pasta fusilli, I did the 3 topologies, or the second one, the double helix one, they can be one-handed. I mean, if you look at I don't know, if you check it out here I'm sure that is the same in the United States, is only one-handedness. It doesn't go with the right-handedness. It goes only with left. How we can create them in the laboratory? There are many different ways. One of them is doing the holography, taking the beam that you want to create and a beam that is a reference, let them interfere together. This is what you will get, is a pitchfork hologram that you can see in the upper side. And if you illuminate it with the reference beam, essentially in the first order of diffraction, you will get the beam that you wanted. Of course, this is very inefficient, I would say, even if you create a phase hologram, which requires a lot of chemistry, that you have to do the bleaching the films and etc. That does not go more than 25%. So and moreover, it only controls the phase. It does not control the intensity. And this was the reason that Enrico Santamato and we developed a technique that we call the perfect technique to simulate, to engineer both intensity and phase, or amplitude and phase. And you can see on the right side that the hologram that we have is not a hologram that extended to entire space, is only picking up certain regions in the plane. And in the first order of diffraction, you will get the beam that you wanted. And we compare these with different techniques, and that essentially will give you the beam that you wanted, or single photon with more than 99% fidelity. But of course, this is also inefficient because you are selecting only a certain region of the hologram. You are not taking the all regions.
So just
yes.
a quick question for you. So because orbital angular momentum is spanned by an infinite dimensional space, when you take the Fourier transform, how do you get a mutually unbiased basis if you've set your initial basis only to say 7 states or your 8 states without populating the entire, without having a.
So indeed, what we do, this is one of the mutually unbiased bases. I talk about that when I go to the quantum communication. Is that okay?
Yeah.
I will explain there.
Sure.
But yes, it's a very good question. Essentially, what we do, we generate them independently. If we say that mutually unbiased basis 1, this is the way that you create them. If it's a mutually unbiased basis 2, number 2, this is another different technique that you create them.
Okay.
And detection as well. So, then the other techniques is, for example, this is what I developed in Canada in group of Bob Boyd, was plasmonic surfaces. So there was nano antennas, really small nano antennas in the dimension of 80 nanometers scales. You put them in a certain topology. If you look at the topology, you will see they look like L-shaped nano antennas. You place it in a given plane, and you give a topology to that. And if you look at the Panchayatma-Berry phase, when you eliminate with left superposition, you will get right-handed superposition. But due to the topology that you have written, you gain a phase. So the total angular momentum is conserved, but it forms from superposition to other superposition, and you gain another additional one. So this is what you see on the lower illustrations. Or you can have liquid crystal topology that you can not only create orbital momentum, but create any beams that you want. Like, for example, 80 beams in the laboratory, or, for example, creating what we call the superposition of L equal to 400 to minus 400. So you can really go with the high dimensionality that you expect. And by the way, that works not only with the laser, but also works with the single photon, at the single photon regime. And this is one of the ability that we have in the laboratory, that we can create anything that you want essentially in the laboratory with the liquid crystal technologies. So one of them was magic plates. So it was a puzzle that was resolved by Sir Michael Berry way back, I think, in 2005. And later on, he extended to a plate. And we say that can we create a flat version of this? And just to tell you what is the magic plate or magic mirror, essentially, in East Asia, more than 3,000 years ago, there were mirrors that they were developing them, and they crafted the back of the mirror such a way that when you look at it, you don't see anything. You see only yourself. But as soon as you eliminate it with light, and if you go to far regions, you will see hidden images like what you see in the lower case. And that was a puzzle for several thousand years until Michael Berry realized that essentially what you need to do, take the image and do the Laplace transform of that, and you will get a very gentle phase variation. Then when you place it on the back of the mirror, you don't see it in the first glance, but it requires propagation, and the image will appear not in a plane, but in a volume. So we use the liquid crystal topology and the technology. And for example, we created the logo of the GG, which is a soccer team, but sorry. Yes, soccer team, that case is true. Soccer team of University of Ottawa. And we expanded over, let's say, a centimeter plane, and we got up to 6 micrometer control in phase. That's the phase. So essentially, that's the reason that you don't see that huge that images, because it's a very smooth changes in a wide range. And then you will get what we call the mirror phase profile. And then we imprinted on the liquid crystal device, and we were able to create, for example, logo of SQO team, which is my team, University of Ottawa, or the GG team within a volume. So that also gives us the possibility to create an image, not in a plane, but in volume. That is a difficult task for usually when people, they want to have presentations and they have to control the overhead lenses. And moreover, it has a rich physics because people, they can look at singularities, the point of singularity that they are formed. So in this case, they will show up as a chaotic topology. Talking about, let's say, intensity and phase, now I'm going to the polarization of light. So as I say that while polarization is bidimensional space, you can map it on a Bloch sphere. That is what solid state people, they do, or you can map it on a Poincare sphere, and you will get, for example, left-handed, right-handed on the North Pole, or you can get HV, which they will be on the X direction, or anti-diagonal, diagonal that will be on Y direction. These look like the mapping of SU2 group onto SO3 group, which allows you to map a two-dimensional object or the two-dimensional space into a surface of sphere. So there you can have left-handed polarization, right-handed polarization. This is what we know. So if you look at the beam, at the tip of electric field, it moves on a circle, either clockwise or counterclockwise. And if you look at the Stokes parameter, there's the Stokes parameter, they are 0. Stokes parameter of 1 and 2, they are 0. Or if you look at the general scenario, you will get elliptical polarization. Well, nothing is surprising so far. But also you can have a linear polarization, which that I showed with the line. So S3 is equal to 0. Mathematically speaking, the two C-core polarization, when you have S1 and S2 is equal to 0, those are singulars. What is singular? We have no idea about the major and minor axis of the polarization ellipse. So this we call it singularity. And moreover about the orientation of those in the space. And linear polarization also is singular because we have no idea if the light is the electric field is moving on the left direction or in the right direction. It oscillates in both directions. So this is what we call it the singularity. The first one we call it C-core polarization singularity or C points, and the last one we call it linear polarization or L lines. And this is one of the examples of the rich topology that you can create them in the laboratory. I can create this beam that has these topological and let's say depolarization topologies. And you will see that on the blue circle, you have linear polarization. So we call it L line. And at the center, you have the C-core polarization. If you let them, the beam to propagate, the topology will stay constant. It may rotate, but it will not change in topology. But what you will get, the C points become the C line, and L points becomes the L surface, which embeds the singularities there. John Nye looked into, John Nye and Michael Berry, they looked into the quantization of them, and they found out that there are three major polarization topologies, and they are Lemon, at which they hold the 1 divided by 2 topology. So if you look at, for example, major axis of the polarization on the Lemon one, if you do a full rotation, you will see that if you do a full rotation, it comes to pi divided by 2, and if you rotate it completely, it becomes pi. So upon a full rotation, the major axis rotates only pi, while the full rotation is 2 pi. So the division of these two will be 1 divided by 2. If you look at the star topology, look at the major axis, do a full rotation, it becomes like this, and then becomes like that way, and finally it becomes again pi rotation, but in counterclockwise way. That's the reason that you will get minus sign for them. And the same for the Mond star. So you can have the ability to create them. I think we were among the people that we developed these techniques at the first hand. Of course, Maya Soskin in Ukraine that passed away, also he developed these techniques. And the question that I ask myself is that what is happening if you take these two topologies and let them focus? And if you focus them, what you will see that the beam goes beyond the paraxial approximation. It goes to the full vectorial mode, and you will get also the Z component of the electric field. But locally, if you look at the polarization ellipses, they are in 2D, but if you put them all together, you will get a Mobius strip for them. So this was, I think, resolving this puzzle after 7 years that was suggested by Isaac Front. And this was done with my collaborators at Max Planck, Peter Benzer, and Gerd Lutz, that they developed this technique that you can have another particle and you can look at the scattering of them, forward scattering and backward scattering, and then you can reconstruct the three-dimensional topologies there. So, and moreover, we ask ourselves, can we translate, let's say, from the 2D topology, again, going to the three-dimensional way, can we create a knot topology? So, and the result was yes, we can create this polarization in the laboratory. So you can have different point of singularity. For example, these three, they are C points, but they are lit like lemon. And these 3 points, if you see in pink, they are look like the star topology. And if you let them propagate, what they form a knot in the three-dimensional space. So that was among the first knots, the first knot in with polarization. And that was done with the collaboration of my colleague, a very good mathematician, Mark Dennis. And And later on, we ask ourselves, can we also create figure 8 knot? And that was again, yes. And you can look at the surfaces that gives you the minimal interaction. This is what we call it, the cipher surface, and looking at the number of holes that you can create them. And then you can match them with the theory. This is one way that people can verify if whether these topology that you created are valid or they are wrong. And I think that was published in Nature Physics way back. And later on, we ask ourselves, can we combine the knot and Mobius? And we call these the frame knot. That came from a question that Avishai and Eli, they asked me at that time in Crete, which I think we made a couple of you there. And later on, we were able to create the frame knot, the first frame knot ever. And the question that people, they ask me, well, I know that if you create a knot, like let's say my tie, they are robust. Are those knots robust or they are very fragile? And students, they told me, no, they are extremely fragile in the laboratory. And I say, well, this doesn't match with the theory that we know. So one of my students, Nazanin, tried to systematically characterize those knots and look at the perturbation that she applies to them. So creating the knot and verifying them and then adding different phases to them, these different distortions, like a Zernicke polynomial.
After or before the creation?
After creation. And then what she realized that she applies this kind of perturbation, I think up to 4 Zernicke polynomials, if I'm not mistaken. And then what she realized that those knots are really robust against all of those perturbations. Of course, you can break them in a certain case when the knot, this, let's say, Zernicke distribution, this Zernicke polynomial is applied only to certain regions, not applied to the entire of the region. And also how much is the phase jumps? If is it going to be 0 to 1 pi, or it's going to be 0 to pi divided by 2. And this is what she found, that no, the knots are really robust, and that was published last year. And moreover, with Eli and Avishai, we developed a technique that people can use these knots to do classical communication, something like RSA protocols. And first we developed the one-way communication, and later on we developed the bi-way communication.
So then they would be really robust to information against many forms of like depolarization.
Absolutely, absolutely. And that was essentially what she showed, that even if you have turbulence, which will be the subject of my talk later on, also these knots are very robust against the no turbulence. So right now we are developing some masks that can project and tell us if you have a cinquefoil knot or trefoil knot. So we can use them for classical communication in a noisy channel. A very, very good point. Yeah.
Very nice.
And then we went from, let's say, phase intensity to polarization. And the last question was that, can we also do the frequency? And the answer was yes, if you can have frequency of omega combined with frequency of 2 omega coherently. This is what people, they say that you will get nothing, but essentially if your detector are quick enough, you can see that the electric field, the tip of electric field moves on a Lissajous pattern. And we say, can we move it out of the plane? Then we added with 3 omega with a different polarization, and we were able to create a zoo of knots in the laboratory. Why they are useful? Because you can explore the 3-dimensional Berry phases in solids. So that I will talk about that in short. So being in Ottawa and next to Paul Corkum and Bob Boyd allows us to also transfer these topologies not only at UV and also at the visible range or infrared, but also going to XUV. So transferring them from, let's say, 800 nanometers to almost 15, 20 nanometers, which the optics doesn't exist there, the proper optics there. So this process was done with a high harmonic generation. First, we showed that while orbital momentum is conserved during this process, later on, we showed that also we can manipulate the polarization. And later on, with Sean leads another project there in 2020, which was published in Nature Photonics. We showed to the people that also when you interact one of those cases of, let's say, azimuthal vector beams to a solid state, you can create a few Tesla magnetic field locally there. And there were a few other works that I didn't want to include here, that also you can create nanostructures, and also you can explore the dichroism of the material. So if the material is responding to one of the handedness better than the other handedness. So, well, now I move from the classical regime and I bring all of them to the quantum regime. So we can create them in the laboratory. This is what I talked about that in details last week. So you can transfer them from a process that we call it parametric down conversion, going to a nonlinear crystal. We expect that there is a conservation of the parity and angular momentum. Then these high dimensional topologies can be transferred to biphoton creation, to entangled photon pairs, and then we can characterize them in a proper way, reconstructing the density matrix. As I said last time, also these very, very time consuming. It may take about a week to reconstruct the density matrix fully. So that was the reason that we developed the biphoton digital holography, which essentially we interfere them in a biphoton scenario with a reference beam, and we record on two different detectors at the same time with a time resolution of 2.5 nanoseconds between each single pixels. So essentially we have 256 detectors that each of them, you can look at the correlation between them within 2.5 nanoseconds. And if you do the proper post-processing, you can reconstruct the phase matching, or you can reconstruct the entangled photons. And instead of, let's say, spending a week, now you can do the reconstruction in less than 3 minutes. And this is what I say, that this was a big mistake of mine, having a yin yang. I don't want to talk about it. I removed that slide. And it went viral only because of my mistake. So, and later on, very recently this year,
but maybe I can interrupt just for a second. It wasn't a scientific mistake. It was a publicity mistake.
Publicity mistake, exactly. So some journalists, it went viral in CNN, BBC, all of those medias, and they say that entanglement observed for the first time in the form of yin-yang, which was wrong, okay? And this year, just published in PRL, we showed that, well, you can create single photons, two entangled pairs that point, if you have detectors, proper detectors, point by point, you have different Bell states. You have psi plus, psi minus, or phi plus, phi minus, with different phases there. And that was a wonderful experiment that one of my students, she performed. And recently, we have also the cloning machine that we built up for doing these high-dimensional cloning, apart from orbital momentum in 2017. So, and then why we care about them? Because they have a quantum application. That was the answer to John, which I will explain to him this evening, of course. So you can create, let's say, you can use the 7-dimension or 7 alphabet as sending information. So the psi1 is one of the mutually unbiased bases. If you do QKD, usually you need more than one mutually unbiased basis. So you need psi1 and psi2. Each of these two, which you can see on the top left corner, they are mutually unbiased bases. If I take one of those sets and I project on the psi1, I will get 1 divided by 7 probability. But psi1 modes, they are orthogonal to each other, and psi2, they are also orthogonal to each other. So I can randomly choose one of these two bases. I send the information there, and Bob performed the measurement randomly, and security comes from this, that you can look at the shared key between them, or share mutually shared information between Alice and Bob, and potentially with Alice and Eve. And you can look at the cases when these two explicitly Alice and Bob is higher than Alice and Eve, the potential of a Strober. And then you can have the chart that I showed to you. So if you go to a higher dimension, the error introduced by Eve can be handled way better. So, and we performed so many different experiments, and one of them was looking at building up a setup that does the QKD without human interface. So, and the machine can pick up which QKD protocol they have to perform, and at the end you can verify them. So we checked the CHAO 15, BB84, tomographic protocol, Singapore protocol, and many others. And we look at the cases where this high dimensional brings a benefit. And later on also, which I will show, that we did attack by using a cloning attack, assuming that Alice and Bob, they are doing the QKD, and I'm the Westroper, and I have a optimal cloning machine. I'm getting information from this setup. And what we realized that for that current setup, at that time in 2017, dimension 4 was the best scenario. You cannot use more than 4 alphabet. Why? Because the imperfection in the detectors causes problem for you that you cannot distinguish from Eve's interceptions. So people, they have done the pool party, doing the QKD in a swimming pool. They have done a roof party, doing the QKD in the between 2 buildings at the University of Ottawa. They have done in the Ottawa River through underwater for submarine applications, and also in a flume at NRC, which we were able to send information through water for more than 30 meters. All of them, they were among the first one of doing high dimensional quantum key distribution in different channels, explicitly in free space, underwater, in the river, in a controlled environment. And also we had the chance to get a specific fiber from Boston University that we were able to send information in high dimensional fashion through the fiber. And one of the main issues that always we see is turbulence in the laboratory. Even underwater, we have turbulence. And recently we have conducted an experiment which is under review, that we created turbulence in the laboratory, and the effect of turbulence will be distorting the information, so producing a huge crosstalk. We were able to characterize them with the Shah-Hartman. This the way the Shah-Hartman works. You have a lot of micro lenses, and then that is aligned in such a way that you focus on the CCD camera. As soon as you go with the plane wave, it focuses at the center, but if you go with the deformed wavefront, it will be focusing in different places. Then you can understand how much is the distortion, and it will provide you the wavefront. On the other side, we have a very fast deformable mirror, which they are pistons that they are moving mirrors around without making them on and off, just they are making different phases. And these two, they were communicating in a fast fashion, more than 3 kilohertz. That was the communication. So in these 3 kilohertz, the turbulence between even 5 kilometers will be frozen completely for you, such a way that you can analyze them and you can compensate it at the same time. But what you need a reference laser that doesn't carry any information, is only sent to monitor the turbulence in the environment. And what we realized that this is extremely important, because even it improves the coupling to a fiber. If you have a fiber and you want to couple it due to the vibration, also this coupling, you have a misalignment, which is within few microns. But if we turn on the adaptive optic system, even it helps you to couple it to the fiber in a better fashion. And this is what we claim, that also this is useful for people that they do quantum key distribution, even with polarization. So I hope, yes, we try to do QKD up to dimension 10, and we show significant improvement with adaptive optic system. On the left side, you will see what we call the process matrix of the channel. When you have a channel and you look at the channel, how this channel is trustable. In the case that you have adaptive optics off, you will have a huge crosstalk depending on the dimensionality. But as soon as you have the adaptive optics on, it reduces the crosstalk due to the turbulence of the channel. And previous cases, we were not able to go more than dimension 4. The free space QKD that we have done was with the polarization degrees of freedom. We were able only going to dimension 4 without adaptive optic system. Now we can easily go to the dimension 10. Back in 2017, we built up 2 domes, let's say free space links at the University of Ottawa between NRC and University of Ottawa, 5.4 kilometers. This was the CAD designed by one of my students, and then we went there and we built up the sheds there, and we placed the optical devices there, and we performed QKD. And just to tell you that also you can see them with the Google Earth right these days. Is a low quality there, but not on my screen. I can see in a high quality here. The red line is the line that let me pause it. Oops, sorry. It shows that even you can see it with the Google Earth that these two, let's say, points, and we had a plan to extend it to 3 points, 3 nodes, to do Alice, Bob, and Charlie experiment. And you see, well, unfortunately, yeah, it's between this building at the University of Ottawa, and you will see the line going to the other side, which is at National Research Council, Canada. Yeah. And right now, well, I will stop here because, yeah. We have centimeters there, which we are monitoring the turbulence in real time. And recently we recorded for 1 year. And this is the data that we have for the turbulence. The green regions, it shows the regions that we can compensate. We are okay without adaptive optics. The blue regions are the regions that we can compensate with adaptive optics, some of them, not all of them. And also at the same time, we develop a deep learning technique such a way that you can also predict the turbulence. We train the system entirely for 1 year. We have the data for each minute, and then we train, and we can tell you within 6 hours if the channel is okay to do the QKD based on recording the temperature, recording the pressure, and the amount of the sunlight that we receive or rain that we receive there. Well, I will move from these to structure massive particles. So this was entirely photons. I think in about 15 minutes, I will talk only about the structured electrons and structured neutrons. So that was what I learned when I was a master student, PhD student. I developed in the field. Then suddenly, after a very interesting paper by Konstantin Belyuk in 2007, we realized that whatever we talk about photons can apply to electrons as well. So you have a wave function, not a problem. You can go to relativistic regime. You deal with Dirac equation, assuming that there is no potential, by the way. If you go to non-relativistic regime, this is what you will get. It's a free particle. It's a Schrödinger equation. For those people that know optics, this is exactly Paraksha wave equation. Whatever we know from optics now applies to free particle, including orbital angular momentum. So I can have an electron, a free electron, that these free electrons can carry angular momentum, orbital momentum, or radial number, or the longitudinal index. That equation is given in the lower side. So essentially, you have access to all of those Hilbert space. But there is a huge difference. Electron has a rest mass and has a charge, which photon doesn't have. So if you look at the electrons, what you will see, if you look at the charge density and the current density, essentially, if you create electrons that carries orbital momentum, then you will get a magnetic moment along propagation direction, which is in addition to the spin degrees of freedom. If you have a spin, of course, you will get mu b with a 1 divided by 2 sigma mu b, either in positive or negative direction, which I will talk about that. But in this case, you will get unbounded magnetic moment for the free electrons, which is given by L E h bar divided by 2m along propagation direction, or -1. So that was amazing for the people that they were in this interesting field. And there were a couple of back-to-back papers. We were a little bit slow at that time. I think by 1 year, we were slow, and people, they got it in Nature, that they create a faceplate. Then they were able to create holograms for electrons, and we created the electron holograms that you can place it in the electron microscope, and you will get electron beams that carries angular momentum. So just to give you a naive perspective, it looks like hydrogen atom taking the nucleus. You have an electrons in the free solutions that carries angular momentum, and angular momentum is not bounded by only S orbit, but also you can go to higher orbits. Why we care about that? Because it provides you many solutions. One is that it gives you the possibility to look at the magnetic properties of material. If you have a material that is unknown to you, you can send these electron beams around it, and it gives a Harlow-Bohm effect, and you can detect them. On the other side, also it can be used to solve serious puzzles in physics, like Strenge-Lach problem. I'm sure that you know about the Strenge-Lach. Myself, I didn't know until 2007 that there is no Strenge-Lach for free electrons. If you say free electrons to a Strenge-Lach device, does not sort it at all. It only works for atoms. It works only for ions and atoms. For mercury or silver, when you take one electron, and you will see the action of missing that one electron there. But it has never worked for a single electrons. And that was the reason that I proposed essentially at that time the Q filter, that it does the permission that spin will be coupled to orbital momentum. I cannot sort the spin of electron, but I can sort orbital momentum of the electrons. And later on in 2017, with my colleagues Vincenzo Grillo and Gerlitz and Miles Paget, we developed a technique that can sort orbital momentum in electron microscopy. And this is one of the pictures of those holograms, that was a part of the Q-sort project. Essentially, we are talking about non-structured writing. So just having an idea, our air is about 100 micrometers dimension, but you have to bring it down to nanoscale writing. So the diameter of this hologram is about 100 microns, so it's about our hair dimension. So you have to make those phase jumps there. We were also able to develop different techniques with Raphael and his team, that we can use the electric field to shape the electrons. That was a different version of a Harlow-Bohm effect that applies to electric field. And with this technique, we were able to apply only few volts and creating orbital momentum of up to 10 units. And that's a dimension of the plates that you can see it on the upper side, which is about 5 microns in dimension. And later on, with our friends Fabrizio and Gianmaria, Vincenzo, and the gang, essentially, Ido Caminier, we were able to look into the way and building up a microscope that allows you to look at the interaction of electrons and materials, such a way that when you illuminate the materials with electric field, you can probe it with electrons. And you can see what is happening within 100 femtoseconds on the electron charge densities. And this is one of those beautiful images that we were able to get to transfer some of the quantum state from the light, which is coming from the lower aperture from the condenser, to electrons, which is coming from the cathode. And we were able to, this is the way that you can look at the surface plasmons there, essentially looking at the quantum state of the electronic states in the surface within almost 100 femtosecond regime. So you can look at them. And finally, just to give you a closing, well, that also applies to neutrons. People in Waterloo, pushing, they were able to transfer orbital momentum also to neutron beams. And one of the questions that I had at that time was that, well, neutron has a mass, doesn't have a charge, only has a spin. Why we care about this? And I was in a flight that I was thinking deeply about this, and I was reading one book, old-fashioned book, and I realized that, well, neutron has a net zero charge, but has internal structure. And if you look at the quarks, and if you look at the charge distribution inside of that, neutron at the center is negatively charged. And if you go to the periphery, you will get the positively charged, and etc. This is what they call it form factor for electric field and also for the magnetic field inside of neutrons. So essentially, if the neutron is moving, it looks like a pancake that at the center has a negative charge, at the periphery has a positive charge, and negative and positive. So I say, well, that's beautiful. And there are experiments about that in PRL and physical UC, which people, what they do neutron scattering, and they look at the far field distribution of that, and then they can tell you what is happening with this form factor, and is it challenging in the field of high energy physics. So I say, well, why not? Let's neutron to be twisted, doing a little bit of mathematics, And finally, what we realized that if you twist it and if you look at the charge distribution of the neutron, due to the Karimi orbital momentum, will get an extra magnetic field. And this magnetic field can be in a range that you can detect them. And this was what we proposed in 2018 in initial physics paper. And I will stop here. There are a lot of things that I can tell you about that, but I can tell you that for the future, what I have in mind is one, building up a quantum microscope, a smart quantum microscope in the photonic regime or in the electronic regime, integrating an attosecond laser to an electron microscope will give you the possibility to look at the interaction of electric field with the material like polymer, even if you bring high energy enough to do the ionization, and seeing what is happening with the polymer, with the molecule, with an atom, with a time resolution that is in order of attoseconds. And you can even look at the way that how, for example, a virus responds to a chemical material upon the time and finding out new technologies, or even looking at the chips, how the chips can be manipulated with electric field, building up very quick chips, or spintronic field, how they are interacting with the magnetic field essentially, or building up a microscope that they are based on entangled photons or multi-entangled photons. So this is one way that I like to develop, and is towards the low dose measurements, both implementing the classical and quantum technologies, exploring the dynamics of the electronic structure, and also improving the resolution. That is not a big challenge for electron microscope, it is a big challenge for optical one, improving the resolution by implementing some quantum measurements or using quantum sources. Building up novel devices. I did not talk about the quantum walks. This is what we have done. We built up quantum simulators that allows us to simulate, let's say, periodic structures, something like a benzene molecules or aromatic structures, or looking at the nanotubes or 2D materials or 3D materials. By them, it's a completely different subject. And also, of course, requires liquid crystal and electron beam lithography. And this is what I'm involved in Canada, also building up a prototype of Quantum Internet Canada. So building up different protocols, different platforms, exploring different environment, doing communication between submarines and satellite, removing the eddy current on the surface, or we have a lot of sensors on the ground which we need to extract the information from them, not necessarily in the quantum fashion, but also in the classical way that you can extract them. Just to give you a statement there, the information that we have about the Mars is way, way higher than the information that we have from the ocean. We have no information about the ocean, essentially. And finally is science. Science is about tackling fundamental questions and curiosity. So there is another field that we developed over the past 7 years, how quantum mechanics works in the general relativity perspective. So how the quantum communication will happen in that range, because I strongly believe that with what I see about human, we go beyond the galaxy. Okay, it may take many generations, but it will happen. And there are a lot of physics that we have no idea about that. And other examples that I gave is solar luminescence. Is a different talk. I don't want to talk about the solar luminescence, about the topology that always gets my interest. So with this, I will finish the talk. And I have to thank all of the people that they helped me to understand those questions and answering them. Some of them, of course, some of those questions that we answered. Many graduate students, many of postdocs, and many of those people that you see in the lower side, they are right now professors, associate professors, or full professors in different universities, from Finland to Israel to Saudi Arabia, China, Qatar. Well, I'm looking around just to see if, oh, yes, also in Germany. And some of them, they are in industry business right now. And colleagues that they help me to understand and doing great science together. So I don't want to name them explicitly. Vincenzo and Rafael and Gert for electron microscope. Going to the quantum communication, Chabad was the main person, Ben Sassman, Duncan, and of course Bob, Miles, and Gerd, Paul Corkum, and all of those great scientists. So thank you very much.
Ebrahim, questions? Yeah, the thought.
Yeah, thanks for the nice talk, Ebrahim. I was wondering when you talked about turbulence detection, are you looking at the whole temperature pressure profile throughout the channel, or?
No, well, the distance is about 5.4 kilometers essentially. So the temperature is not uniform. Turbulence is coming from change of density. How do you get the change of density in air? It's changing the temperature. So you can have local heats, and then you will get turbulences. And these local heats, they are changing upon the time because it's a non-dense material, it's not a solid one, so it's air. So it's a gas one, so it moves around, and then you will get the dependency, the time dependency. No, it's not a one single temperature, and is upon, let's say, many different phase elements. But the turbulence can be translated in three classes. One is very big turbulence that essentially you don't need compensation. A medium class turbulence, which is what we are looking for. And we have a strong one that you cannot do anything with it. And they have a different physics, by the way.
Okay, other questions? Could you tell us a little bit more about your optical knots? So you're mentioning that you have this robustness is what you'd expect from a knot topology, but you said if you did something, you can snap the knots. So how can you tell us a little bit more about that? Under what conditions you have robustness?
So this is the case if you look at the left side, let's say, okay? So we have three kinds of topologies. One of them is a loop, is two loops, okay? Which is a link, essentially. The other one is a trefoil, and the last one is a cinquefoil. And there are parameters on the upper side, is S and A, how much is the window of the distribution and the perturbation that you apply, and how strong they are, okay? And if you go down and down, you will see different Zernicke polynomial that applies to them. So I can take the knots, I can apply the phase tilt, so it's kicking the phases to be like that way, and that way is moving in the opposite way. And then you can see what is happening with the topology. And what we can see that even going to half phase jump, a full phase jump, still this topology is stable.
So one of the proposals for doing robust quantum computation is to use topological features in your quantum states. Have you ever thought about trying to take this to the quantum regime and doing robust quantum computing with your knots?
Well, we have brought this to the quantum regime, but we have not thought about doing the quantum computation with it. This is something like a quantum money, for example, is one choice that they can use the knots to build up, right? No, we did not look into that.
Okay, let me know when you get that quantum money going. I can invest in that.
Okay.
All right. Any other questions or comments? All right. If not, let's thank Ebrahim again.